now you will be part of it, rocketing beyond the horizon of our time to join the greatest human adventure of all time.
Now, Science Fantastic.
Welcome back to Science Fantastic with Professor Michio Kaku. On Science Fantastic, not only do we profile some of the most amazing discoveries in science and technology, we also throw the lines open. Here's your chance. Okay, well, let's throw the lines open. Let's take the first listener phone call. Hello. This is Science Fantastic. You're on the air. Any comments or questions?
I was just curious of how the way that the dogs as in animals have evolved over the years. Did they come from wolves, or how did they all come about? And the different breeds, how are we mixing breeds and getting all these different variances of animals over the years? Thank you.
Well, you ask a very intriguing question that's being answered even as we speak by geneticists who are beginning to sequence the DNA of dogs. Well, first of all, we know that dogs were domesticated roughly 10,000 years ago. 10,000 years ago, that's when the Ice Age melted. We forget that before then, during the peak of the Ice Age, most of North America was under a half a mile of ice. Well, after the ice melted, agriculture gets off the ground slowly, civilization, villages start, and that's when we began to domesticate dogs from the wolf, Canis lupus. And that's one reason why dogs of any breed can breed with any other dog, because they're all descended from one species, Canis lupus. Now, when scientists began to sequence the DNA of dogs, they found something very interesting. They found out that there was just not one branch of lineage, but several branches depending upon where you were on the planet Earth. So in other words, not once, but many times, different populations of people domesticated the dog and then began to breed the dog for their own particular purposes. That's why we have such a bewildering variety of dogs for specific purposes. Some dogs, for example, are good at shepherding sheep. Others are hunters. Others are simply good companions. That's why we have such a multiplicity of dogs. And dogs, of course, don't live very long. Dogs age much faster than us, about 5 times faster. So you can imagine how fast evolution has taken place, that we have bred the dog for just 10,000 years. Then you can even calculate roughly how many generations of dogs there have been since the very first dog. You just divide into 10,000 years. Now, not only this, but because dogs begin to be bred by humans and then we begin to interbreed dogs, that's the reason why dogs suffer from many genetic mutations. It's very sad. But if you have a dog, you begin to realize that as they age, they begin to exhibit many of the genetic mutations, their feet, their digestive system, cancers. They begin to show different kinds of genetic diseases because of all the inbreeding that took place. So in other words, man's best friend has in some sense paid a price. The benefit of domestication is that there are more dogs today than wolves. So from an evolutionary point of view, bingo. It was actually a success story for the dog because there are more dogs than wolves. But the price that dogs pay for this is that they are essentially riddled with genetic mutations, many of which begin to show themselves as they begin to age. Okay, well, let's take the next listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
My name is Eric, and I'm calling from Corpus Christi, Texas. 1440 Keys. And my question is, can we build, or have we already built, atomic-powered aircraft? I'm wondering if this aircraft could maybe describe what we've seen in the skies and don't have a true idea of what it is. And I'm wondering if maybe this might be the atomic-powered aircraft might be what we're looking at.
Well, Eric, you ask a very interesting question because my advisor when I was young, starting in high school, was Edward Teller. Edward Teller was the father of the hydrogen bomb, and he was a very vocal proponent of putting nukes everywhere. Nukes not only to carve out canals between continents, but also nuclear power plants in aircraft carriers, submarines, rockets, and airplanes. So let me tell you a little bit about the secret history of this, which is rather interesting. Back in the 1950s, the United States military and government very seriously looked at the possibility of putting nuclear power plants, not just in submarines, which was a smashing success, but also in rockets and airplanes. In fact, there was a project called the Kiwi. The Kiwi is a flightless bird, and was aptly named because it was basically a nuclear rocket on a railroad track. So when you threw the switch, the ignition took place. All of a sudden, you had all this exhaust coming out one end, and the nuclear rocket would go barreling down the railroad tracks. Well, there was some problems. First of all, the reactor tended to be unstable. It tended to melt down. There were problems with maintaining the reactor, and the military eventually gave up. They said it's simply not worth it. For the cost-benefit analysis, they're simply not getting the bang for the buck. And the same thing for the airplane. It turns out that, yes, in principle, you could put a nuclear power plant in an airplane, and the airplane could go around the world many times. But simply refueling a jet, turned out to be much more cost-effective, not to mention the fact that if the rocket crashed or if the airplane crashed, you would have a nightmare. Can you imagine a nuclear power plant landing in someone's backyard? The contamination would be enormous. And in the 50s and 60s, the military had some experience with this because there were several broken arrows during that time. An arrow is jargon for a nuclear weapon. A broken arrow is a bomb that literally falls out of the bomb bay of a bomber. There have been a number of incidences where atomic bombs accidentally landed on South Carolina, North Carolina, off the coast of Georgia. And this, of course, was a huge embarrassment for the military. So we actually did have nuclear materials literally falling from the sky in terms of nuclear bombs. So, again, some people think that maybe, just maybe, flying saucer sightings are actually secret military craft. Well, who knows? We do know, however, that the military deliberately led the public to believe that sightings of the stealth bomber may in fact have been UFOs to cover up the fact that the military was experimenting with stealth bombers or bombers that can deflect and diffuse radar so they don't have much of a radar signature. But basically, the reason why the atomic airplane was shelved was because it was not that safe, it was unstable, and basically not that cost-effective. Simply refueling would give the range needed for airplanes to go pretty much around the world. Okay, well, let's take the next listener phone call. Hi, this is Science Fantastic. You're on the air. Any comments or questions?
This is Jessica from Corpus Christi. I'm listening to station 1440 AM. And my question is, who was the first person to think, like, okay, I'm going to eat whatever comes out of this chicken's butt? Well, basically I'm talking about an egg. But, like... Who would have thought?
Okay, well, let me try to take a crack at that question. I think your question is in two parts. First of all, who was the first person to have a light bulb emerge over their head and say, oh, gee, that looks pretty delicious, an egg. Maybe I'll grab that egg. And then, of course, everybody wants to know which came first, the chicken or the egg. Well, let me take a stab at it. First of all, the first person to look at an egg and decide to eat it was probably not a person at all. We descended from the apes, according to the theory of Charles Darwin, and apes eat eggs. In fact, if you go even further back in time, mammals were once reptiles. Mammals, in fact, are an offshoot of the reptiles, and reptiles eat eggs as well. So the answer to your question is very simply, there was no first human who looked at an egg and said to themselves, well, gee, this is a great meal, because it goes back even before humankind was born. If you go all the way back, even primitive animals will eat eggs of other animals. And then the other question is, which came first, the chicken or the egg? And the answer to that is probably neither. The chicken and the egg probably emerged from a more simpler form. You realize if you go way back into the past, now 2 billion years into the past, you just had microorganisms on the planet Earth that simply underwent mitosis, that is, splitting apart. It took billions of years for these germs, these bacteria, to create concrete organisms that then began to lay eggs and then began to differentiate. So to answer your question, there was no first human who spied the first egg. And which came first, the chicken or the egg? The answer is probably neither. Okay, well, let's take the next listener phone call.
Hi, my name is Daniel Hensley, and I am calling from Pensacola, Florida. And I am talking from News Talk 1370, WCOA. My question is, spirits and everything, are they really matter? Like ghosts, can they actually become matter, or are they just like, is this like something of your brain? Is it like...
Okay, well, you ask a very ancient question that goes all the way back to the dawn of civilization. Take a look at any mythology from any society, and you'll see myths of spirits and ghosts and stuff like that. Well, as a scientist, we can only say a few things. Science is based on what is reproducible, measurable, and testable. That's the foundation of science. If you have a scientific result, it has to work all the time. It just can't work on Tuesdays or Thursdays, but not on Wednesdays. It has to be eternal. Well, when it comes to ghosts and things, we find a problem, and that is they're not reproducible. They're not testable. In fact, they're not even falsifiable. How can you prove or even disprove the existence of ghosts, demons, and spirits? So scientists are kind of at a loss at this point. However, that doesn't mean that some scientists haven't speculated about these things. So let's mention two possible speculations. One speculation, as you mentioned, is that they are perhaps figments of the imagination. Another is maybe they're from another dimension. If they're a figment of our imagination, then it turns out there should be a part of the brain which induces this kind of behavior. In fact, there is. It's called epileptic lesions. In fact, we've had guests on radio talking about this. It turns out that a certain lesion to the brain, a stroke, an injury, a blow to the brain, will actually set off these epileptic lesions, in which case you feel that you're in the presence of a spirit. Anything that happens, you think that something is behind it. These people, for example, when they're interviewed in hospitals, say that when it rains, it's because there are evil spirits that are punishing you. That if you fall down, it's because you did something bad that day. So any event that happens, there's intentionality, evil, or a spirit behind it. And you can even induce this with radio. It turns out there's an electromagnetic transmitter. Time Magazine even did a story on it, where if you shine this radio to a certain part of the brain, you can actually induce this effect so that you feel like you're in the presence of a ghost or a spirit. Richard Dawkins, who I met a few months ago in Mexico at a conference, he's an atheist from Oxford University, a leading atheist. So some people had the bright idea of putting him in this contraption. So they put radio waves into his brain to see whether or not this confirmed atheist would say that, yes, there is a God. Well, after Professor Dawkins came out, he said, nope, I didn't see any ghosts at all. However, there is another theory that says that maybe ghosts are from another dimension. Let's say that you have a tabletop where there are people living on a tabletop, flatlanders that are squashed in two dimensions. If you are standing above the table looking down, then the flatlanders cannot see you. You are invisible. But you could perform all sorts of magic tricks. You could put your finger right through the table, the surface of the table, and the beings on the table would see a sphere, a circle of flesh as you stick your finger in it. You'd be able to peel these people off the table and make them float, so they would disappear off their universe, and you can put them back. So in other words, if we are nothing but flatlanders living in a flat universe, then somebody from a higher dimension could disappear, reappear, reach into our stomach, perform surgery without cutting our skin, and do all sorts of magic feats that are usually associated with ghosts. Well, I don't know. All I'm saying is that theologians have written about the possibility that maybe ghosts live in a higher dimension. Many of my books, like Hyperspace, talk about the lore that goes back. But, hey, I'm a scientist. I won't believe it till we can reproduce it in the laboratory. Okay, the lines are open, so let's take the next listener phone call. Hello.
Jim Sanders, Pensacola, Florida, listening on WCOA Radio 1370 AM. If the Big Bang happened 13.5 billion years ago and things are rushing away from that point, then isn't there a whole lot of nothing between that point and the edge where we are expanding away like a big bubble?
Okay, well, you ask a question that a lot of people ask when they first hear about the Big Bang theory. If the Big Bang means that eventually we came from a point, and we are 13.7 billion years away from that original point, then first of all, where is that point? Is it in the constellation Virgo, the constellation of the Big Dipper? Where is that point? And are we spinning away from that point at a very fast velocity? And as you point out, is there a gap? Well, think of a balloon. Think of a balloon, and we are like flies on flypaper. We're trapped on the surface of the balloon, and the balloon is expanding in all directions. Okay, got that? Now, if you ask, let's say, an ant walking on the surface of this balloon, where did the balloon originate from? Where was the original expansion taking place? Well, the ant would say, well, nowhere. Nowhere on the surface of the balloon did the expansion take place. The balloon is expanding away from the point of origin. So, in other words, the Big Bang, in some sense, happened everywhere and nowhere. There is no point on the surface of the balloon that is the origin of the Big Bang. So if you ask the ant, then where did the expansion take place? The answer would be, well, it's off the surface of the balloon. But since the surface of the balloon is everything there is, the whole universe is the surface of the balloon, then the Big Bang took place off the surface of the universe. In other words, in hyperspace, in another dimension. So that's the simplest way to realize that you cannot point to one particular point in the night sky and say that's the point of the origin of the universe. So if you were around 13.7 billion years ago, what would you see? Back then, the universe would be very small, smaller than a bowling ball, smaller than a ping pong ball, smaller than an electron. And as it expanded, you would ask a question, well, where is the Big Bang? And the answer would be everywhere. Everywhere you look, you would see radiation. It'd be very hot, quite radioactive. Everywhere you look, you would see essentially the origin of the Big Bang. Now, you may say to yourself, if it's that abstract, then how do we even know it's correct? Well, we have photographs of the Big Bang. Pictures, baby pictures of the infant universe. Go to nasa.gov and look under WMAP, W-M-A-P. That's a satellite which is photographing the explosion itself. Believe it or not, the explosion is still reverberating around the surface of our balloon. So let's say the balloon is expanding, but there are ripples on the surface of the balloon because the origin was so violent that it created shock waves. Well, we can photograph these shock waves, and by golly, it looks like an explosion. This is called the famous microwave background radiation. The radiation of the Big Bang is quite cold now. It's in the microwave range, 3 degrees above absolute zero, and you can photograph that radiation. And in fact, when you have a radio or TV and you get that static on your radio, some of that static actually comes from Genesis. So believe it or not, you are actually listening to creation itself. The static, that buzz you hear on radio, some of it comes from Jupiter. The planet Jupiter emits a lot of radiation, but a lot of that radiation also comes from the origin of the universe itself. Okay, I think we have time for another listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
Jonathan, I am calling from Inglewood, California. I'm listening to you on Freedom 970. And I don't think that time exists. Can you tell me whether or not you believe it does?
Well, some people say space, time, maybe it's all an optical illusion. Maybe time doesn't really exist. Maybe space doesn't exist. Well, that's when we have to define things, because without definitions, we're just spouting words into the vacuum. And, when you define time, you realize that time is a way to measure change. When things change, we need a way to measure that change, and we call that time. So obviously things change. The very fact that you could even ask that question is a consequence of the fact that your muscles can move, your mouth can move, and the radio waves can go across space, and I can listen to it. So the very fact that there is change means that there is time, because time is nothing but a way that we have of measuring change. Now, Shakespeare, I think, had the best way of looking at it. Shakespeare said that the universe is a stage. Everything around us is nothing but a stage. And we are actors making our entrances and exits on the stage of life. Well, this stage is space. We are matter propelled by energy. And the way in which you measure change along the stage of life is time. Now, of course, things get very complicated when Einstein comes along, and he shows that there's really a four-dimensional structure. That is, space and time are really, in some sense, part of a single fabric, a fabric that can stretch and bend. So in other words, not only is there time, but there's also space, and that space and time are part of a larger entity called space-time. Matter and energy are also part of a larger concept called matter-energy. And that's the relativistic way, the Einsteinian way of viewing the universe. Well, let's take the next listener phone call. Hello, this is Science Fantastic. You're on the air. Any comments or questions?
Hi, this is Steve. I'm calling from Tucson, Arizona. I know that hair on our body is essentially a dead organism. When you cut a hair, there's no nerve. Yet hair seems to know how long to grow. The hair on my arms does not grow as long as the hair on my head. If I shave the hair on my arm or leg, it only grows back a certain length. How does the hair know how long to grow? Thank you.
Well, Steve, you ask a very interesting question, which had enormous commercial implications because, of course, as baby boomers age, they lose their hair, specifically on the top of their head. And so baldness is going to be one of the targets of biotechnology. In fact, recently it was announced that we're unraveling some of the genes of baldness, and that in turn could give us real, not fake, but real cures for baldness. Well, first of all, let's talk about what is hair. Hair, believe it or not, is protein. As you pointed out, it's not alive in the usual sense of the word. It is protein, not the kind of protein that builds muscle, but nonetheless a form of protein. And hair left to itself will simply grow infinitely long. There are certain peoples who don't cut their hair, and their hair grows on to be very long. But hair also falls out, and that's why certain hairs on your arm and places like that don't simply get longer and longer. It's not that the hair suddenly shuts itself off. The hair falls off, and new hair grows, and it gives the illusion that the hair suddenly knows when to stop. Okay, well, let's take the next listener phone call. Hello.
My question is, why can't NASA use old technology that's been proven from the 70s and a design that is ultra safe and ship some of this nuclear waste out towards the sun, charging, of course, the nuclear power companies a high premium, not only in America, but in France, in Germany, and where they're having all these problems with the nuclear waste, make their own money and therefore turn that money over and fund missions that they would like to run but can't because they can't get money from the government.
Well, you ask a question that actually has some very deep answers to it. At first, it sounds like a no-brainer. Nuclear power plants generate nuclear waste, so why not simply send it to the sun? The sun is the ultimate garbage can, right? Well, there are some very big practical problems which have prevented this from happening. First of all, booster rocket failure takes place about 1% of the time. That's right. When our brave astronauts don their spacesuits, they know that 1% of the time they may not come back. These are former fighter pilots, former military people. A lot of them know the risks of going into space. If you calculate the number of disasters, for example, on the space shuttle, we've had 2 horrendous accidents, each one killing 7 brave astronauts, then the odds came out pretty much right on the dot. 1% of the time. 1% of the space shuttle shots and ended in tragic failure. Now, you can imagine what would happen if nuclear waste were on one of these rockets. Sure, you're right. Many of the shots would go to the sun. We can do that. So you say to yourself, well, why not send all the waste into outer space? Well, there's several problems. One, of course, is booster rocket failure. 1% of the time, as Isaac Newton said, what goes up comes back down, usually on somebody's backyard. And the ecological implications of that would be horrible. Can you imagine a Chernobyl from outer space spewing all the radioactive waste? But there's also a more mundane, practical problem, cost. It costs about $10,000 to put a pound of anything into orbit. Forget going to the sun. We're just talking about spinning wheels around the Earth. $10,000 per pound. Get on a bathroom scale and weigh yourself. Well, if you're made out of solid gold, if your body were made out of solid gold, that's the cost of what it would take to put your body into orbit, $10,000 a pound. Now, to send it into the sun would cost more like $100,000 a pound to send it into the sun. So you see, there's some real problems with regards to cost. And then, of course, you have the other problem, the sheer amount of nuclear waste. Every reactor produces about 30 tons, not pounds, 30 tons of high-level waste per year. And the United States alone has about 100 reactors. So do the math. 100 times 30 tons per year, and you realize the enormous amount of nuclear waste just generated by the United States alone. And France, hey, something on the order of 70% of their electricity in France comes from nuclear power. So you know that the French have an even larger commitment to nuclear energy than us, and that means an enormous amount of waste. And how long do we have to guard it? Tens of thousands to millions of years. That's incredible. The half-life of uranium-238, for example, is 4.5 billion years. That's the age of the solar system. The age of the solar system is the half-life of uranium-238. Now, by law, the United States government has stated that radioactive waste should be sequestered from the environment for 10,000 years. That's why in Yucca Mountains outside Las Vegas, we were going to put our nuclear waste. But the Yucca Mountain site has been canceled by President Barack Obama. Why? It's unstable. 10,000 years ago, we had an ice age, for God's sake, an ice age. How do you predict these things? How can you make sure that nuclear waste does not encounter ice and flooding over a 10,000-year period of time when the last 10,000 years, most of North America was under a half a mile of ice? Well, the headache proliferates on and on. Now, we physicists have thought about all these things. There's even an issue of the Journal of Modern Physics, which goes through the options. Another option was to put it under the seabed, inject it directly into the tectonic plates. Well, that sounds like a great idea. Tectonic plates are stable for millions of years, so why not simply shoot the waste beneath the plates? Well, the conclusion of physicists was that we know not that much about earthquakes and the surface of the Earth. We know even less about the bottom of the ocean. So injecting nuclear waste on the bottom of the oceans would be a nightmare with unpredictable results. Yet another possibility was shoot it in salt domes. Well, we tried that in Lyons, Kansas. Kansas was supposed to be the site where we would put nuclear waste, but then it turns out that we didn't know that the Lyons, Kansas was used by wildcatters, and there's like holes drilled by them that have unknown locations. It's like pockmarked, like Swiss cheese. Well, as you can imagine, for all these reasons, we simply don't know what to do with the waste. Well, unfortunately, that's it. Once again, this is Science Fantastic with Professor Michio Kaku.
Science Fantastic with Professor Michio Kaku.
This is Science Fantastic with Professor Michio Kaku. On Science Fantastic, we profile the amazing, jaw-dropping scientific discoveries which are revolutionizing our world and touching our lives. And in this hour, once again, we're going to throw the lines open because this hour is your hour. Let's take the first listener phone call.
Hi, this is Brad from Palm Bay, Florida, WMEL. And my question is, if you hit a tennis ball in space, would it just go on forever, or is there such a thing as space dust that would slow it down? Thank you.
Well, you ask a question that has bedeviled scientists for generations, so let me try to answer that question. First of all, in outer space, there's no friction. Therefore, an object, in principle, will go on forever, according to Newton's first law of motion. Isaac Newton said an object in motion stays in motion forever unless acted on by an outside force. Now, you ask another question. That outside force, could it be space dust? And the answer is, well, yes, there is space dust out there. In fact, the Earth moves in a wind of space debris left over from ancient meteors, left over from the formation of the solar system. And that means the Earth gets heavier. In fact, you can actually measure how much heavier the Earth gets. Every year, the Earth gets several tons of this space dust that it encounters. So the answer to your question is, well, yes, for both. In other words, an object in motion will stay in motion indefinitely, but it will encounter space dust. Space dust is quite rare, quite rarefied, so it's not going to cause the object to slow down immediately. So the object will actually move for billions of years in free space. And so sometimes in science fiction movies, you see the astronaut being thrown out there into the abyss, and you ask a very concrete question. The hero just got thrown into outer space. If he's not captured or rescued, for how long will he drift in outer space? And the answer is forever. That is, he'll go on until, of course, he goes to the end of the universe. Now, then the next question is there an end to the universe? Is there a brick wall that says, stop, do not pass go, do not collect $200, this is the end of the universe? Well, if that's the end of the universe, then what lies on the other side of the end of the universe? And so you get into all sorts of philosophical questions. Einstein asked these questions to himself because Einstein thought that the universe was like a bubble, a soap bubble. We live on the skin of the soap bubble, and the soap bubble is expanding, and that's called the expanding universe theory. Started with a Big Bang. And the next question is, if you throw a tennis ball in the bubble, does the tennis ball ever hit an end to the universe? Think about it. If the universe is a bubble, and you throw a bubble or a tennis ball in one direction, it keeps on going in that direction until it comes back to where it started from, in which case that tennis ball will hit you on the back of your head. So the tennis ball will go on indefinitely, but it'll simply repeat itself as it goes around the universe. And so one possible universe is that the universe is a hypersphere, that if you throw a ball in one direction, eventually it'll come back and hit you in the back of your head. Now, if you have a telescope and can see the farthest star and the farthest object in the universe with a telescope, what would you see? The farthest object in the universe would be the back of your head. Now, is that really a description of our universe? We don't know. At the present time seems to indicate that the universe seems to be infinite, but we need more data. And this is being argued by physicists even today. So, to be quite frank, most physicists would say the universe seems to be limitless, but we're not sure at the present time. Okay, well, let's move right along to the next listener phone call.
My name is Brian. I'm calling from Utah on 1430 AM. Is it possible to have a planet, an Earth-like planet, twice the size of Earth, or maybe an Earth-like planet possibly the size of a Jupiter? Thank you.
Well, these kinds of questions about super-Earths are being asked by astronomers even as we speak. So far, we have found about 3,600 planets orbiting other stars, and we think that on average, for every star you see at night, there is a planet going around it. This is incredible. It means that the average star system has at least one planet going around it. And what kinds of planets are they? For the most part, they're Jupiter-sized. They're gigantic gas giants, very similar to our Jupiter. But we're now beginning to see Earth-like planets as well. These are called super-Earths. They tend to be bigger than the Earth by about 50%, maybe 100%, but they're very Earth-like, and they are in the Goldilocks zone. That is, they are just right to have liquid water. Not too close, because then the oceans would boil. Not too far from the sun, because then the oceans would freeze. But they are just right to have liquid oceans. And why is liquid water so important? Because that's where life began. Water is the universal solvent. It dissolves most chemicals, including hydrocarbons and, of course, DNA, and that's where we think life got off the ground. Then the caller asked a question. Can you have Earth-like planets double the size of the Earth or Jupiter-sized? Well, first of all, let me say yes. These super-Earths could be 50%, maybe 100% the size of the Earth. They may even have liquid oceans. We're not sure. But in principle, they lie in the habitable zone, the Goldilocks zone of the mother star. But can an Earth-like planet be the size of Jupiter? Well, that answer is no. Because it turns out that the Earth and these super-Earths are probably as big a rocky planet as you're going to get. Beyond that, you start to get gas giants like Neptune and Saturn and Jupiter. So once you start to get to that size, the size of Jupiter, you basically become what is called a gas giant, composed of hydrogen and helium gas. But to be a rocky planet like the Earth, you have to be either maybe the size of the Earth or maybe 100% larger, but not much more than that. So we've now logged 3,600 planets orbiting other stars in the solar system, and we do find about 20 of them or so that are very much Earth-like. They're super-Earths, maybe 50 to 100% bigger than the Earth, but once you get bigger than that, you start to become a gas giant like Jupiter. Okay, let's move right along to the next listener phone call.
It's Alex from New York. My question was, if I were to throw water on a grease fire, it would just make a bigger fire. Why is it that happens?
Okay, well, water is quite interesting because if you have a skillet and you heat it to a very high temperature and you take one drop of water and put it on the skillet, normally you would expect it to vaporize immediately. But no, it doesn't. What happens is there's a layer of steam, of steam that forms between the water and the skillet, and the water droplet then floats on top of this layer of steam, and it does not vaporize at all. And you can do this right now. Go to the kitchen, turn it on, heat a skillet to beyond the boiling point of water, and put a drop of water, and you see the water goes skidding around the surface until finally all of it vaporizes. Now, don't do this because, of course, you could get injured. But if you were to drop a lot of water on a hot skillet, it would splatter immediately because steam would form, and steam could be explosive. And so do not do this in your kitchen. Do not pour a glass of water on a super hot skillet because the water could vaporize immediately, and steam can be rather explosive in that situation. In fact, when you have a nuclear power accident like at Chernobyl, a lot of the damage was done not by uranium blowing up like an atomic bomb. No, a lot of the damage at Chernobyl was done by a steam explosion. Because when cold water hits hot melted uranium, you get a layer of steam forming, and a lot of it is explosive, And in fact, at Chernobyl, it blew the lid. It blew the lid right off the top of the reactor, and roughly 30% or so of the uranium and the waste in the core vaporized and was sent into space. And so you realize how dangerous steam explosions can be. Steam explosions also happened at Fukushima, which blew the top right off 3, not 1, not 2, but 3 nuclear power stations. And so once again, when water comes in contact with hot metal, steam forms, and on a small scale, you can use steam in order to see droplets of water go skidding around a hot frying pan. But in large quantities, it causes steam, which can be explosive, and that's why it splatters. And if you have a sufficiently large amount of steam, it'll literally blow the lid off a building. So I do not think you should do that experiment in your kitchen. Okay, well, let's move right along now and take the next listener phone call.
My name's Emily from Kansas, and my question is there such thing as the possibility of like a zombie virus or an illness that could take over the human race? Thanks.
Well, you ask a question right out of the movies. Is there such a thing as a zombie virus that can take over the human race? Well, at the present time, we know of no virus that can create zombies, and we certainly know of no virus that can take over the human race. However, that said, there is a possibility of viruses that can infect the human race and perhaps even destroy it. For example, take HIV, the AIDS virus, and realize that it's not airborne. That is, if you sneeze, you cannot spread HIV. But we know the genes. We know the genes that can make a virus become airborne. Now let's say you weaponize the HIV virus. That is very bad, because at that point you may be able to make HIV airborne. Now the HIV virus is very simple. It only has about 9 genes. 7, 8, or 9 genes. Very small number of genes make up the HIV virus. So if you were to insert the genes that make a virus airborne into HIV, you now have a virus that in principle could destroy 98% of the human race. Just by sneezing, you can then infect people with a virus which is more or less incurable until some of the recent drugs that have now come on the market. Now, first of all, why could it kill 98% of the population and not 100% of the population? It turns out that 2% of people, especially Europeans, are immune to HIV. This was rather shocking. You could actually inject them with HIV and they will not come down with AIDS. They are immune. So scientists investigated why is it that 2% of Europeans are totally immune to the AIDS virus. Well, we think we know why. The AIDS virus has to have a docking site on the surface of a cell in order to latch onto the cell and then infect the cell. It has to have what is called a docking site on the surface of the cell. Well, it turns out that 2% of the European population are lacking the docking site for HIV. Very interesting. And scientists, geneticists have said that something happened. Something happened several hundred years ago. A mutation spread within the European population that made them invulnerable to certain forms of viruses. Those that didn't have the docking site survived. Those that did have the docking site died. Evolution at work among the human race. Well, what virus attacked the human race several centuries ago that could wipe us out, that allowed this mutation to survive? This mutation, as I said, makes you invulnerable to HIV. Well, some people say it's the Black Plague. So now we have a rather interesting picture. The Black Plague wiped out up to 50% or so of European people. That's huge. 50% or so of the European population died because of several successive waves of the Black Plague. This means that evolution therefore favored people that didn't have that docking site, that could be infected with the Black Plague and didn't come down with the Black Plague. That mutation is still with us today. Today, of course, it's dropped in numbers down to about maybe 2%. But yeah, some geneticists say that perhaps the reason why 2% of the human race of the European population is invulnerable to AIDS is because they are the ones, the lucky ones, that had that mutation hundreds of years ago, and the Black Plague accentuated and allowed that mutation to survive. Well, there's no zombie virus, but we do know that HIV could be weaponized to infect the entire human race, and that could literally wipe out Homo sapiens as we know it. Okay, well, let's get right to the next listener phone call.
My name is Hirschman. I'm calling from Irvine, California. My question is, at what speed does gravity travel? For example, if it was the middle of the night and somehow the sun disappeared, it just vaporized, went away, how many minutes, hours, seconds later would we feel this on Earth? Thank you very much.
Great. That's a great question. The answer is 8 minutes. If the sun were to disappear right now, the sun were to disappear, a shock wave of gravity would then radially emit from the sun a sphere called gravity waves. A spherical gravity wave would be emitted from the sun. Inside that sphere, you think that the sun has disappeared. Outside the sphere, it has not yet disappeared, so the sphere is a gravity wave, a wave of gravity. Well, just recently, last year, scientists detected gravity waves. This will earn the Nobel Prize for those physicists who backed that project. We now know that disturbances in gravity move at the speed of light. As Einstein said, nothing can travel faster than light, even gravity. Even gravity cannot travel faster than the speed of light. So the fastest velocity of light, fastest velocity of gravity is the speed of light, as we see in gravity waves, and we detected them just as Einstein predicted. Gravity waves were discovered just last year. By the way, gravity waves were first predicted by Einstein in 1916. In 1916, 1 year after he formulated general relativity, he predicted that gravity waves would be found traveling at the speed of light. However, he said they'd be so faint that they're not going to be discovered in his lifetime. So that's kind of a depressing thought, knowing that you have a theory of the universe, and yet certain tests of it could not be done in your lifetime. However, the bending of starlight was done in his lifetime, and that's the reason why he won essentially the Nobel Prize and also the respect of physicists for generations to come. By the way, the Nobel Prize itself was given to him for the photoelectric effect because the people in the Nobel Prize committee could not understand relativity, and they said so. Yes, they could not understand Einstein's crowning achievement because it was too complicated for them. So they gave him the Nobel Prize for a theory much simpler, that is, the theory of the photoelectric effect, which makes possible television and lasers. Let's take the next listener phone call.
This is JJ, and I'm on Navarre Beach in Florida. My question is, I would like to hear a little bit more about the idea of the poles reversing. I've heard, didn't know they expect it, but what will be the consequences? Thank you.
Okay, well, if you saw the movie The Day After Tomorrow, it probably scared the pants off everyone who saw that movie because the poles shifted, the Earth was moving on its axis in an irregular way, continents began to move, and doomsday was staring us in the face. Well, that's a Hollywood movie. Let's get to the facts about what's happening with the Earth. First of all, the Earth has not one but two poles. It has the magnetic pole, where the North Pole is in Canada, and it has the geologic pole, and that pole points toward the North Star, Polaris. We're talking about pole shift that is magnetic. So that could happen without destroying the planet Earth. If the geologic poles were to shift, that would really destroy the planet Earth, and we don't think that's going to happen. But the magnetic pole shift is happening even as we speak. That's right. If you take a look at ancient manuscripts from the mariners, they recorded the strength of the magnetic field. we cannot compare that with the magnetic field strength of today, and we find that it is diminishing. That's right. The magnetic field is getting weaker and weaker even as we speak. This is a statement of fact, not fiction or Hollywood movies. However, it does not mean the end of the world. We expect the poles, the magnetic poles, to completely flip, perhaps in the next few hundred years. Okay? It's not going to happen anytime soon. And we know that this has happened many times in the past. How do we know that? By looking at Hawaii. By going to Hawaii and digging into the lava flows, when lava freezes, the direction of the magnetic north is frozen in the lava. So if you dig in the lava, you go many, many feet into the lava, you go back into the past. And sure enough, as you dig into the lava flows, you see that the direction of the North Pole has shifted over the thousands to millions of years that you can record by digging into the lava flow in Hawaii. So we do know that, yes, the North Pole has wandered. It has definitely wandered. What happens is the North Pole begins to weaken, then shuts off completely, and then the poles start to shift. And we know this because we can dig right into the lava flows, not just in Hawaii, but elsewhere as well. So we're headed for another pole shift. The next pole shift will take place maybe in a few centuries, maybe a few thousand years, but it's not the end of the world. Because we're not talking about the geologic pole, we're talking about the magnetic pole, and it has shifted many times in the past. So you don't have to take out your insurance policy. You don't have to worry about doomsday. But yes, the poles are going to shift in the next few hundred to a few thousand years. Okay, well, let's take the next listener phone call.
My name is Lisa. I'm calling from Clovis, California. My question is, I had a near-death experience, and in that experience, time almost did not exist. And I just wondered, how do you explain those near-death experiences, and how do you relate it to science in terms of time travel? Thank you.
Okay, well, in my book, The Future of the Mind, physicists and doctors have actually studied near-death experiences to see whether there's a physical basis to many of these things. The United States Air Force, for example, has been very curious about near-death experiences because people who have them say that there is a light at the end of the tunnel. Well, let's talk about this. The Air Force puts pilots in centrifuges, and as the centrifuges spin faster and faster, blood drains from your brain and you black out. That could, of course, cause multi-million-dollar airplanes to crash. And so the Air Force has studied this effect very carefully. They put pilots in a centrifuge, spin them faster and faster, and then tune the velocity of the centrifuge just so that the pilots begin to black out. And guess what they see? A light at the end of the tunnel. After the break, I'll explain precisely how that happens, and also is it possible to leave your body? We physicists have studied that phenomenon as well, and can time slow down? We've studied that one as well. Let's take a short commercial break, and after the break, I'll talk about the light at the end of the tunnel, I'll talk about leaving your body, and I'll talk about near-death experiences. Welcome back to Science Fantastic with Professor Michio Kaku. Well, before the break, we had a call about near-death experiences. Thousands of people have had them. These are reputable people. These are school teachers, ministers. And why did they have these near-death experiences? Well, we don't know, but scientists have studied what might explain these near-death experiences. When the Air Force puts pilots in an ultracentrifuge, blood drains from the top of their head and they black out. Very important, because you could crash and multi-million-dollar airplanes and the lives of the pilots are at stake. What they found was as follows. As you get faster and faster in ultracentrifuge, blood drains from your eyes. Therefore, the outside layer of the retina drains blood first. Therefore, you black out. But the process of blacking out means that the outside of your peripheral vision gets larger and larger. The center of the eye gets smaller and smaller, so you see a light at the end of the tunnel, because that's where blood is still moving inside your retina. Blood has drained from the outside of the retina, that's why it's black, and the center is still there, and that's why you see a light at the end of the tunnel. Also, you can induce this effect with lack of oxygen. The presence of carbon dioxide will also cause this effect. Many effects will cause a blackout, and just before you black out, you see a light at the end of the tunnel. Also, near-death experiences include out-of-body experience as well. This can be induced using a probe on the brain. It turns out that you have parts of the brain, one lobe that controls eyesight, another lobe that controls balance. And if you get an electrical probe and you probe the boundary between the two lobes of the brain, you can induce out-of-body experience. The body gets confused. One lobe says you are feeling seasick. The other lobe says, no, I see what's outside and I am stationary. So the brain gets confused when you stimulate the boundary between the lobe that controls eyesight and the lobe that controls balance, which is located near the back of your head. And then the body tries to understand why it's getting these conflicting signals, and the brain says, I understand, we are floating. We're floating in the air, and we can look back. We can look back at our unconscious body. In fact, Richard Feynman, winner of the Nobel Prize, one of the greatest physicists of the last 50 years, put himself in an isolation changer and induced this effect. And he said, yes, it's caused because the brain gets confused, and that's why you think you are floating in midair, which is an effect that you can induce when the brain is exposed, and you can touch the brain in two spots simultaneously. And so for all these reasons, we physicists believe that, yes, near-death experiences are very difficult to explain, but one way to induce many of these effects is to either confuse the brain or deprive the brain of oxygen. Also, time seems to slow down. Now, why is that when you have a near-death experience? Well, I once hosted a show for the Discovery Channel where we did an experiment. We got a daredevil. We put him on a bungee jump apparatus, and we put him backwards, and then we kicked him off backwards, and then he fell in free fall. Now, with him, we put a timer that's electronic, so he could see the numbers go real fast. 1, 2, 3, 4, 5, 6, 7, real fast as he was flying backwards. Now, of course, you get a sense of dying as you fall backwards when you bungee jump in the wrong direction. But when he looked at the numbers, 1, 2, 3, 4, 5, moving very rapidly, we asked him to identify the numbers. It turns out that when he was stationary and we asked him to read the numbers on this dial, he could not. Because the numbers, 1, 2, 3, 4, 5, moved so fast, he could not identify the numbers. Then we pushed him backwards when he bungee jumped, and then he read the numbers, and by golly, time slowed down. He could actually read the numbers, 1, 2, 3, 4, 5, as they were moving on this dial, this electronic dial, very rapidly. He could read the numbers. So what does this mean? Did time really slow down? The answer is no. Did the perception of time slow down? Yes. It turns out that the brain actually speeded up. So it gave you the illusion that you could see numbers moving extremely fast, and that's how you explain the fact that some people think they see their life moving in front of them. Everything seems to slow down when you experience fear. My brother once, for example, was in a car accident. He saw the car in front of him as he was about to hit the car, but he was helpless. He was like trapped in a movie, he said. He could see the car in slow motion coming closer and closer. He knew there was going to be an accident, but there was nothing he could do because his muscles could not react fast enough. But his brain clearly saw the car slow down in front of him. So is that science fiction? Is that fantasy? No, it's real. And you can actually induce this effect by pushing people backwards off a bungee jump or making fear the dominant emotion. You can literally induce this effect of time slowing down as you have the sensation of dying. Well, unfortunately, our time is up. Once again, you've been listening to Science Fantastic with Professor Michio Kaku.